Hello, this is Sadbir. The topic of our discussion in this video is column space of a matrix. The column space of a matrix is defined as the linear combination of all the columns. For example, if a matrix A 1, 2, 3 and 4, then the column space, which is sometimes denoted by COL of is all the possible linear combination of the vector 1, 3 plus beta time vector 2, 4, where alpha and beta, they are real number. Similarly, if we have a matrix 1, 2, 3, 4, 5, 6, then the column space of this matrix will be the linear combination of space alpha 1, 4 plus beta 2, 5 and gamma 3, 6. One more example of a matrix, this time say 1, 2, 3, 4, 5, 6. This is a 3 by 2 matrix. Then the column space of this matrix is the linear combination of alpha of this vector 1, 3, 5 plus beta time the linear combination is 2, 4 and 6. This column space is a subspace of R2 because this vector 1, 3 and the vector 2, 4, this vector and this vector, they are both belongs to R2. So this column space is the subspace of R2. Similarly, the column space of this matrix is also the subspace of R2. Again, the reason is this vector and these vector which are generating this column space, they are going to be the part of R2. So this is R2. However, this subspace is the subspace of R3 because this vector and this vector, they are both in R3. So one thing to notice that the column space is not just contains this vector, which are the column vector. It is the linear combination of all the of all these vectors. So the column space contains a lot more element or a lot more vector than the column of the matrix. So in these slides, we will learn the geometrically view of the column space, and we will take some examples and draw the column space of those matrices. So my first example is a 2 by 2 matrix. So if I draw the column space of 1, -1 and 2, 3, let's see how it is going to look like, how big column space is this. So these are the two vector, which is a 1, -1. So 1, -1. And this is another vector, which is going to write 2, 3 here. Then as you can see that this vector V and this vector W, they are not parallel. So if I take the linear combination alpha time V plus beta time W, they are going to generate the whole space, whole R2 space. So if I take the linear combination alpha V plus beta W, it is going to generate the whole space R2. So then you can say the column space of the matrix A in this case is whole space R2. As you can see that if I take any linear combination, let's suppose if I take alpha and beta both is equal to 1 and I draw the parallelogram, this vector is gonna be in R2. Or I take a different scale of alpha, the vector V and W, and then I plot the parallelogram, and then basically this is going to be the vector in the column space of A. So if I keep choosing alpha and different alpha and beta and keep drawing these parallelogram and calculating the diagonal of this parallelogram, eventually this whole diagonal are going to fill my R2 space. Now let's take another example. So suppose I have this matrix 1, 2, and this is a 2, 4. Now let's look like how the column space, geometrically the column space of this matrix is going to look like. So if I draw the vector 1, 2 here, and then the vector 2, negative 4 is the same, it goes in the same direction, but it is a double in the magnitude. So this vector is a 2, 4. So as you can see that if I take the linear combination, any linear combination of these two vectors, and the diagonal is always going to be, if I draw the diagonal of the vector 1, 2, and 2, 4, they're always going to be stay on that line. So in this case, the linear, since the column space, the linear combination of this vector and that vector, therefore the column space is a line in R2. Or in other words, you can say that the column space is R1, is just a one-dimensional space because it's just a line. We're going to take one more example. Let's suppose this time we have the matrix 1, 2, 3, and 4, 5, 6, and then this is a 2, 4, and 6. If I draw, because this is a three-dimensional, it's a subspace of R3, so I have to draw the picture in R3. So let's suppose this first column is a V, this is a W, and this is a U. And then you can see that V and W, they are going to be somewhere vector here, or maybe somewhere here in the R2 space. Let's suppose this is a V and this is a W. But the vector U is going to be parallel to V. In fact, is going to be on this line, but this is just the double in the magnitude. So vector is going to be, this is going to be U. Now, if I take all the linear combination, all the linear combination of V and W and U are going to stay in that plane in R2. So in this case, the column space of this matrix A is going to be R2 because it's gonna be a plane in R3, plane in R3. Because these two vectors are parallel, so therefore the column space is just going to be generated by W and V. When you take all the linear combination, it is going to contain all the vector which is basically inside of V and W. So as we can see that if the column of the matrix are not parallel, then the column space is going to be the whole space. But if the column of the 2 by 2 matrix is parallel, then you basically lose the dimension of the column space. You have one less element in that column space. We can generalize this concept that if you have n by m matrix, and then the column space of this matrix is going to be m to the power k, where you have a k columns, where the k number of column of A are non-parallel. So this is the geometry suggests that if the matrix has k columns which are not parallel to each other, then the column space of that matrix is gonna be R2K. There is another note that if you have a matrix A n by n, and this matrix is invertible, this implies all the columns, all n column of this matrix are non-parallel. So none of the column of this matrix is going to be parallel if the matrix is invertible, because this matrix has n pivots. So therefore all the column of this matrix are going to be non-parallel. So, and this implies basically the column space of a matrix which is invertible is gonna be Rn. This is another fact about the column space of the matrix. Here I have one quiz problem for you to practice. Please pause the video for 1 and 2 minutes and work on this problem. Next, we will find what is the relation between the column space of a matrix A and the solution of the linear system AV is equal to B. One of the fundamental question in the linear algebra is for can we solve the linear system AV is equal to B for any B? Unfortunately, the answer of this question is no. We cannot solve the linear system AV is equal to B for any B. So now I can rephrase this question. For what value, for what values of B I can solve AV is equal to B is solvable. So where should I choose my B so that this system is solvable? Now you can look at the system. So B is equal to AV, or in other word, it is a linear combination of columns of A. Because this product of the matrix is defined as the linear combination of the column of A. So B is essentially the linear combination of the column of B. But this is the definition of the column space. So this is the column space of B. So that means if B belong to the column space of the matrix A, then we can solve this linear system. Then AV is equal to B is solvable. So this is our main result of this section is that if you can find B in the column space of A, then you can solve that linear system AV is equal to B for that B. Now, for example, if I take my matrix A is equal to 1, 2, 3, 4, I know the column space of this matrix is the column space of this matrix is whole R2. So I can take any element in R2. So if I choose B is equal to 1, comma 2, I know that this system AV is equal to 1, comma 2 will give me a solution, is solvable. Now let's take another example. The matrix 1, 2, 3, 4, 5, 6, 2, 4, 6. I know the column space of this matrix A is R2 from the previous discussion. So if I want to solve this system, my B has to be something like this, 1, 2, 0. So my B has to be in R2. So the Z component of my B has to be 0 in order to solve this system AV is equal to B. So the B must be in the column space if you want to solve this linear system. And on this discussion, we can also conclude one remark basically that if you have a matrix n by n matrix and this matrix is invertible, then you know that the column space of this matrix A is going to be whole Rn. So it means you can take any B from the space Rn and then you will have the system AV is equal to B solvable. So that's why the column space of the matrix is really important. If we know the column space of the matrix, we would know that which linear system is soluble and which linear system is not soluble. In this video, we only learn how to calculate the column space by using the geometry of the problem. In the next video, we will learn a more analytically way to calculate the column space. Here I have one last quiz problem for you to practice. Please pause the video for 1 and 2 minutes and work on this problem. I will see you in the next video. Bye for now.